Today we are going to revise the topic propagation of sound waves. So let's start. Sound is a form of energy, and this energy, what it does, it produces the sensation of hearing in our ears. Anything that vibrates produces sound. Now, all the vibrations we may not be able to hear because human audibility range is from 20 hertz to 20,000 hertz. Less than 20 hertz is called as infrasonic, and more than 20,000 hertz is called as ultrasonic. Human audibility range is also called as sonic, only sonic, okay? Examples of infrasonic: earthquakes, volcanic eruptions, ocean waves, avalanches, waterfalls, meteors, lightning. All these are the examples of infrasonics. Whereas ultrasonic also had wide range of uses. It is used for imaging and scanning of internal organs. Like for example, when we were small, like fetus, ultrasonography is used to examine the fetus during pregnancy. Okay, ultrasonic sound is also used to destroy the kidney stones. They are broken into tiny pieces, which are flushed out through the urine. They are used to detect faults in the metallic sheets. They are used by different animals. Some animals emit ultrasonic sound, example bats. So they are able to find the prey in the dark by emitting this ultrasonic sound, and it is reflected back. So they have that echo depth ranging system in them. So why ultrasonic sound has so many applications? So there are few properties which make them highly useful. The first property is that energy carried by ultrasonic sound is very high. Secondly, it is highly directive in nature. It will not bend along the edges of the obstacle. The way right now I'm talking, the sound is spread in all possible directions, but ultrasonic sound goes like a beam. Hence, these applications. So ultrasonic sound has very high energy as compared to the normal sound, sonic sound, and it is highly directional. We call it as high directivity. Speed of sound in air is 330 meters per second. If anything which can travel more than this speed, we call it as supersonic. Example, Concorde, jet planes, fighter planes. So these are all examples of supersonics. Now whatever I'm going to tell you next is not in portion, that is hypersonic, which is Mach 5, Mach 10. So Mach 5 means 5 times faster than sonic. Okay. So hypersonic missiles are there. Today we are at a juncture where we have high hypersonic, Mach 10 also. Sound is a mechanical wave. What is the meaning of this statement? It means sound needs medium to propagate. Without medium, sound cannot travel. So we call it as sound is a mechanical wave. So two people sitting on the moon next to each other cannot hear even if they scream loudly. The reason? There is no medium. So hence sound needs medium to travel, to propagate. What are the requisites of the medium needed for a sound to propagate? Number one, the medium should be elastic. What is the meaning of elasticity over here? When the particles of the medium are vibrating, okay, once from the mean position, initial position, they are displaced on either side. So after that, they should come back to the mean position. That is called as elasticity. Second thing needed for a medium is it should have inertia, so that particles can store mechanical energy. And the third condition or property needed for the medium is it should be frictionless, so that there should not be any loss of energy when the sound is propagating. Waves can be classified as longitudinal waves and transverse waves. Transverse wave is made up of crests and troughs. The raised portions are called as crests, and the depressions are called as troughs. Whereas longitudinal waves are made up of compressions and rarefactions. So transverse wave is made up of crests and troughs, whereas longitudinal is made up of compressions and rarefactions. Now let us study the definition of transverse and longitudinal wave. If you have a look carefully, transverse waves, the particles are vibrating perpendicular to the direction of propagation of wave. So I am marking in the diagram. See how the particles are vibrating perpendicular to the direction of propagation of wave. Whereas, I'm assuming over here that the wave is traveling from left to right. Okay. So the particles are traveling perpendicular. So wave is traveling like this, whereas the particles are moving up and down perpendicular to the propagation of wave. Fine. In case of a longitudinal wave, the particles are vibrating in the direction of propagation of wave. If the wave is traveling from left to right, okay, like this, then the particles are vibrating like this. So that's the definition of longitudinal and transverse wave. Examples of longitudinal waves: sound in air, primary waves of an earthquake, ultrasound, vibration of a spring, tsunami waves. So these are all examples of longitudinal waves. Now let us look at the examples of transverse waves. Sound waves on the surface of water. The ripples caused on the surface of water are transverse waves, whereas the secondary waves of earthquake are transverse waves. Ocean waves are another example of transverse waves. Another type of classification: mechanical waves and electromagnetic waves. Mechanical waves are the waves which need medium to propagate. They cannot travel without medium. They need the medium. Whereas electromagnetic waves can travel with medium or in medium as well as without medium also. Examples of mechanical waves we studied: sound, whereas examples of electromagnetic waves, light waves. Light travels some part without medium and again it comes in the atmosphere. Medium is there. X-rays, gamma rays, these are all examples of electromagnetic waves. Let's study some terms related to wave motion. Here is the graph of our transverse wave, you can say. The first term we are going to study is amplitude. So what is the meaning of the word amplitude? It is denoted by a symbol small a. Okay. Amplitude is the maximum displacement of the particle of the medium on either side of its mean position. What is the meaning? Let's have a look at the diagram. How much high this particle can go and how much down it can come as per this graph. I'm drawing and showing you. So this particle, how high it can go, okay, or how down it can come, maximum, equal on both the sides. So as per this diagram, how much is it? Tell me. 2 centimeters. Perfect. Down also -2. Minus means it is going down. So it is not that maths wala -2. Okay. So both the sides it is going 2 units up and 2 units down. This is called as amplitude. Its SI unit is meter. Next term is time period, denoted by capital T. Its SI unit is second. What is the definition? Time taken by a particle of a medium to complete its one vibration. How many vibrations? One vibration. Time taken to complete one vibration is called as time period. Exactly reciprocal of this is frequency. Frequency is denoted by symbol small f, sometimes n also, but right now we will be sticking to symbol f. SI unit is hertz, and the definition: the number of vibrations made by a particle of a medium in 1 second. How many vibrations in 1 second? Say 10 vibrations in 1 second, so the frequency is 10 hertz. 100 vibrations in 1 second, frequency is 100 hertz. And how is time period and frequency related to each other? Frequency and time period are reciprocal to each other. Next term is wavelength, denoted by Greek symbol lambda. Same graph, but now on the x-axis we'll be having, instead of time, distance. Say this distance traveled is in meters. So what's the definition of wavelength? The distance traveled by the wave in one time period of vibration is called as wavelength. SI unit is meters. One more definition. For a transverse wave, okay, it is the distance between two consecutive crests or two consecutive troughs. I'll mark and show you. So have a look carefully. Distance between two consecutive crests or distance between two consecutive troughs is called as wavelength. Now how much in this case? Measure and tell me. Okay, 5 minus 1. So answer is 4 meters. In this case also let us check. 7 minus 3, that is 4 meters. Or distance traveled by one wave. What is the meaning of one wave? One wave means one crest plus one trough. I'll shade and show you. So have a look carefully. This is one wave. So how much distance it has traveled? 4. Hence the wavelength is how much? 4 meters. The last term we need to study is wave velocity. We have already done in the earliest chapter also. Speed is distance upon time. Same way, distance traveled by a wave in 1 second is called as wave velocity or wave speed. Fine. Distance traveled by how much? One wave in 1 second. Okay. A wave, single wave is called as wave velocity. SI unit is meters per second. And how is wave velocity, frequency and wavelength related? They are related by a formula V is equal to F lambda. What is V? V stands for wave velocity. What is F? Frequency. What is lambda? Wavelength. Also we can change this to, because frequency is 1 by T, I can also write it as V is equal to lambda upon T. So any formula while doing the numericals is fine. Now speed of sound in different media, solids, liquids and gases. If we compare, speed of sound is fastest in solids, then in liquids, then in gases. So it is slowest in a gas if you compare with solids, liquids and gases. So sound is fastest in solids, then liquids and then gas, least in gas. Okay. Here is the example. Speed of sound in air approximately is 330 meters per second. In water 1450 and in glass it is 5500 meters per second. So clearly it is fastest in solids. Now we are not going to talk about solids and liquids. So the topic is factors affecting speed of sound in a gas. We are not comparing with solids and liquids. Okay, only in a gas. The first factor is density. Speed of sound is inversely proportional to square root of density. Let me explain you with the help of an example. Inversely proportional to square root of density. Less density, more speed. Remember that. Less density, more speed. Okay. Example, oxygen is 16 times denser than hydrogen. So they can ask you, where is the speed of sound maximum or more if you compare in hydrogen or oxygen? Answer is less density, more speed. So hydrogen has less density, but how many times more? So let me show you how to write this. Speed of sound in hydrogen upon speed of sound in oxygen, inversely proportional. So rho is the symbol for density, and if I substitute the values, I'll get density of oxygen is 16, hydrogen is 1. The square root of 16 is 4. So speed of sound in hydrogen is 4 times the speed of sound in oxygen. Understood? Second factor, temperature. Speed of sound in a gas increases with increase in temperature of the gas. So it is directly proportional to temperature, but square root of and the temperature should be in Kelvin scale. They can ask you like a small numerical, or they can ask you an MCQ. I will show you how the question can be asked. Speed of sound in air approximately increases by about 0.61 meters per second for each degree. If I increase the temperature from 20 degrees to 21 degrees, then the sound will increase by how much? 0.61 meters per second. If I increase it from 30 degrees to 31 degrees, speed of sound will increase by how much? So every degree rise, speed of sound will increase by how much? 0.61. Okay. So based on this, we can write a formula where Vt is at that particular temperature, how much will be the speed? Okay. V0, that is the speed of sound at 0 degrees Celsius, and it is rising by 0.61 T. So I'll explain this with the help of one example. Let us say it is given that V0, that is speed of sound at 0 degrees Celsius, is 330. Now the question asked is, what will be the speed at 25 degrees Celsius. So V25 will be equal to V0 plus 0.61 into 25, and that turns out to be 330 plus 15.25. So the answer turns out to be 345.25 meters per second. Similarly, one more example here only will show. Say if they ask you at 10 degrees Celsius, this can be asked in MCQs. So what will be the speed at 10 degrees? So V10 is equal to V0 is equal to 0.61 into 10. So the answer will be, sorry, this is plus 330 plus 6.1. So at 10 degrees Celsius, the speed of sound will be 336.1 meters per second. Third factor is humidity. Speed of sound in air increases with increase in humidity. The density of water vapor is 5/8 the density of dry air. Remember that. That means humid air is lighter than dry air. So we can say that the sound travels faster in humid air as compared to dry air. Fourth factor is direction of wind. If the wind is blowing in the direction of propagation of sound, speed of sound will increase. And if it is blowing in the direction opposite to that of the sound, then the speed of sound will decrease. Next is factors not affecting speed of sound in a gas. Not. That is the important word. So there are three factors. If pressure changes, that will have no effect on the speed of sound. Amplitude also has no effect, whereas wavelength. If wavelength changes, frequency will change. So overall, the speed of sound remains the same. So these are the factors which are not affecting the speed of sound in a gas.